Hi, I'm Hannah Marcus and this is my third Alum video. So here are my crystals. We can see that there are a lot of small crystals on the bottom. The solution right now is really cloudy. Um, so compared to the last time, there are a lot more crystals. So I just threw out the solution so I can comment on the size and shape. If we see, now it's more visible, there's one big crystal and a lot of small crystals around here. If we look into this crystal, it looks really like fragmented, and the reason of this, it's because the evaporation happened too fast. So the temperature might have had an effect, since the crystals have like really changing temperatures between cold and hot. This may have affected the growth of my crystal. In order to grow one big high quality crystal, we needed to consider a few factors. One of them is the evaporation. The evaporation of the solution needs to happen really slowly because we need the lattice to be perfect to form one big crystal. The lattice of my crystal is imperfect, that's why they are fragmented. Another factor we need to consider is temperature, because temperature can affect the rate of forward and backward reaction. We need to look for the optimal conditions that would allow for nucleation while still leading the slow growth of crystals. Also, we need to have a more careful synthesis process that takes into account pressure and temperature. Another thing that could be done to grow a bigger crystal would be having seed crystals on my solution, like doing all the process I already did to create the saturated solution, but then to that solution add seed crystals that would help make a big crystal. This spacing refers to the distance between planes in a crystal. Certain values are assigned to different molecular geometries, which gives scientists clues into the shapes of specific crystals. Also, there is a known relationship between the d-spacing and the wavelength and path length of the X-ray diffraction, which allow us to determine the geometry of the material and then eventually the identity of the material. Also, scientists can build the entire geometry of a crystal based on its d-spacing. To calculate the d-spacing for the most intense peak in the diffraction pattern, I'm going to use this equation. This is Bragg's law equation. In here we're going to take n as 1 because we only are focusing about the center peak. Then the spacing would turn to this. This is given, and the highest peak is around 2 theta equals 20.6 or so, and because it's 2 theta and we only want theta, we divide it by 2 and get 10.3. So by doing the calculations, we get that the d-spacing is 0.431 nanometers, which would equal 431 picometers.